Deep inside the chaotic, pitch-black void of the biological cell, there is a heavily armored vault, the nucleus. Inside this vault sits the ultimate master code, DNA. This genome holds the blueprint for every structure in the organism, making it far too valuable to ever leave its protective casing. The cellular environment outside is a hazardous factory floor, filled with reactive chemicals and free-floating enzymes that would quickly degrade the unprotected master code. To manufacture any physical machinery, the cell has to solve a logistical problem. It must engineer a way to transfer the instruction data to the factory floor without moving the master hard drive itself. Through transcription, the cell unzips a section of the master DNA genome, exposing data for a single required file. It synthesizes a temporary copy, messenger RNA. This acts as a single-stranded biological flash drive. Once finished, the DNA strands zip back together, remaining completely safe. The new mRNA strand slips out through a sharp, geometric pore in the nucleus wall, heading directly into the perilous, open workspace of the cell. The master code is secure, and a temporary, expendable blueprint has been successfully deployed for execution. Out in the dark, open fluid of the cytoplasm, the mRNA flash drive drifts until it reaches the manufacturing hardware. This is the ribosome. It is a massive, two-piece mechanical factory that slams shut around the mRNA strand, functioning as a microscopic 3D printer. The ribosome performs a specific industrial process called translation, where it reads the software script to produce physical matter. It physically moves down the length of the mRNA strand, processing the incoming sequence step by step. Rather than a passive vessel, the ribosome acts as an active, ratcheting engine designed to bridge the digital to physical divide. The ribosome does not read this data as a continuous, flowing stream. Instead, it processes the information in distinct, segmented chunks. This vector breakdown shows how the genetic code is parsed. The strand is segmented into 3-letter blocks called codons, such as A, U, G. For each specific codon, the ribosome selects a corresponding raw material, an amino acid, perfectly matching the active segment. With every step, the machine violently stamps the selected amino acid onto a growing chain, shooting the assembled product out its top port. Through this mechanical repetition, the ribosome successfully downgrades complex digital data into a linear, one-dimensional string of physical matter. Once the ribosome reaches the end of the mRNA instructions, it releases the finished linear string of amino acids. In its current one-dimensional state, this chain cannot perform any physical work. It is essentially a floppy, useless thread. This schematic reveals the underlying physics constraint. Every individual amino acid block on that chain carries a specific electromagnetic charge. Some are positive, some are negative, and some actively repel water. Lined up in the exact sequence dictated by the digital code, this loose chain operates as a loaded spring of volatile, opposing magnetic forces. The exact millisecond the chain separates from the ribosome, those opposing forces interact with the surrounding water and each other. The charges spark and pull across the entire length of the structure. This triggers a rapid physical process called protein folding. The intense electromagnetic pull forces the linear chain to instantly collapse upon itself. This collapse is highly deterministic. The resulting shape is mandated precisely by the original codon sequence. The chain violently jerks, twists, and locks perfectly into a rigid, interlocking 3-dimensional geometric structure, a functional protein, ready to execute its programmed task. Cellular biology operates an end-to-end, highly secure data-to-matter pipeline, turning linear information into structural reality.